The method of undetermined coefficients is something that every undergraduate differential equation student should be exposed to in their undergraduate courses. But it's something that I remember as a student being a little confused over. And every time I saw it in future classes from textbooks and everything, it always seemed like it taught it the same way. And I could see why some people might be confused about it. So I figured I'd make a video just to see if I can offer my own perspective and help clarify things for you. So in this video here, it is about undetermined coefficients, but it's not like an introductory first time you're ever seeing it sort of thing. So there's some assumptions made by me. One is that you could easily solve a differential equation that looks like this. It's a linear constant coefficient homogeneous differential equation. And if you're one of those students who should be able to do that, you would know that you would have the auxiliary polynomial, which is basically just creating a polynomial with corresponding, or the exponents corresponding to the order of each derivative. If you'll remember, it's from making a guess that a solution of this differential equation is an exponential. And that itself comes from something called the matrix exponential, which is way outside the scope of this video. But that's a quadratic equation, so you can just use the quadratic formula, of course. So negative b plus or minus the square root of b squared minus 4ac over 2a. And what the solution looks like depends on the sign of the discriminant. So the sign of that is what determines what the solution looks like. You're either going to have two distinct real roots, you could have one repeated real root, or you could have a pair of complex conjugate roots. So you should know what to do with those. The other thing or the second thing I'm gonna assume is that you can solve this differential equation. So the same left-hand side, but the right-hand side is a function of, we're gonna say the independent variable is x. And I'm gonna say for simple g of x. I always hate using the word simple, but in this case it sort of works. So that could be something like if I said g of x was 5, or g of x was x, or if it was a cosine of x. Those are usually introductory examples you would see for undetermined coefficients, and your notes should provide you with enough information with how to do that. And the third thing I'll assume is that you have an understanding of multiplicity of polynomial roots. So for example, if I gave you the polynomial x minus 1 times x plus 3 squared times x squared plus 1 cubed, you could of course factor that just a tiny bit if you allow for complex numbers. So I'll do that. So that would bring this into an x plus I times x minus I, each of those with an exponent of 3. And you can have a root, and each one has a corresponding multiplicity. So for the first one, the root is 1. There's an exponent hidden there of 1, so that's its multiplicity. The next one, the root is negative 3. The exponent is 2, so it's a multiplicity of 2. And then negative I and plus I both have exponents of 3, so those are the multiplicities. That's just like a quick glossing over it. Basically means you factor the polynomial as much as you can into linear factors, include complex numbers if necessary, and then the multiplicity is just the exponent on each linear factor. Okay, so that's the stuff that I'm assuming that you know, or if you forgot about it, hopefully I just gave you a quick reminder, although we're going to review the second thing here really quickly. So in undergraduate courses, when you do the method of undetermined coefficients, you're always going to have something of this form. A, B, and C are constants. Typically, you usually do this with second order equations, but at the very end, I'll do an example with a higher order equation. g of x is going to involve a polynomial, an exponential, a sine function, a cosine function, or a combination of some or all of those. That's because the derivative of each of these things looks like one of these things. Derivative of a polynomial is a polynomial. Derivative of an exponential is an exponential. Derivatives of sine and cosine alternate between each other with minus signs thrown in once in a while. Okay, so if we've got something like that, it's a non-homogeneous differential equation because the right side, which doesn't involve y at all, is non-zero. We break that solution into two parts, something plus something. The part labeled as yc, the notation doesn't really matter. Your book might call it yh. I think those are the two common ones. But the c is typically stands for complementary, while the h stands for homogeneous. So this is a homogeneous equation because the right side is 0 and all the stuff involving, or all the stuff on the left side involves y. So you would do the same thing. You would investigate that using the method with the auxiliary polynomial, which is described here below. And we did that on the previous slide. Yp, which is for particular, takes into consideration g of x, and it could be affected by yc. Specifically, it's going to be affected by the roots of that auxiliary polynomial. Okay, lots of background information. Always like to get that out of the way so I don't jump right into using some notation that you haven't seen. So this is a typical example that you might have seen for the first time when you looked at undetermined coefficients. I'm not particularly concerned with finding the actual explicit solution. What I find is with students, oftentimes they'll come to me and say, I know how to determine the solution or determine the values of the constants once I already know what the form of the yp is supposed to look like. The trouble they have is actually determining what to make as their guess. You know, with a lot of these problems, it's sort of like you're making a guess, but you're doing so from the perspective of you kind of already know what the answer is supposed to look like. And that brings up some confusion sometimes. So I'm going to concentrate on finding the form instead of going through lists of equations and plugging stuff in and determining values of A, B, and C and all that sort of stuff. That's not the focus of this. So let's try to find the form of the particular solution for 4y double prime plus 9y equals 15. So first of all, you look at the complementary solution, and you do that by looking at the auxiliary polynomial. So remember the coefficients are the same, and the exponent on r is the same as the order of the derivative on y. So you have 4r squared plus 9. That's a 0th derivative there, so it's r to the 0 hidden. And you want to find the roots of that. Subtract the 9 over, divide by 4. So that's negative 9 over 4. Take the square root, you get a plus or minus 3 halves. But because there was a minus sign there in the first place, there's an I. So if you'll remember, quick review, that means that the complementary solution is an arbitrary constant multiplied by cosine of 3 halves of, not 3/3, 3 halves of x plus a possibly different constant multiplied by sine of the same thing. Now, if you wanted to figure out what the particular solution is that takes into account the 15, you make a guess. And your textbook probably told you, well, what looks like a constant? We need to take derivatives, combine them together, add them together to get 15. And they say, well, it sort of makes sense that the particular solution should be a constant itself. And what you do then is you plug that in. You have 4yp double prime plus 9yp should equal 15. And in this case, you take the derivative. The second derivative of a constant is 0. So this is just 4 times 0 plus 9 times a0 equals 15. And you solve for a0 and get 5/3. Now, I said I wasn't going to do this, but this one was pretty quick. I just wanted to outline that. So overall, the general solution is going to be the yc that we found up above plus 5/3. That's your general solution. Remember that this constant here that you make the guess for, a0, that's not an arbitrary constant. You're supposed to find the exact value by plugging in. And in this example, I did that, but let's see, in the rest of them, doesn't look like I'm going to do that. I just want to outline how to figure out the proper guess. So let's do the same thing for y double prime minus 16y equals 2x e to the 4x. How's this one going to be different? Well, first of all, we'll go for the complementary solution. Auxiliary polynomial, you have r squared minus 16, set it equal to 0, plus or minus 4. And of course, that gives you, since they're real distinct roots, arbitrary constant times e to the one of them x plus arbitrary constant e to the other one x. The order doesn't matter. Your c1 could be my c2. You could switch the plus and minus 4. Doesn't matter. So we did those. Now we want to take a look at the particular solution. And you make a guess again. Now this is where, from what I remember as a student, it became a little bit annoying because there wasn't really an outline of how you're supposed to do this in general. It was like you make a guess, you test it. Uh-oh, you don't get a consistent system of equations. So you go back and you adjust the guess, and then maybe it happens again. And I don't like that. I want to try to figure out a way to get the right one from the start. But let's go through how your book might have outlined that. The first thing it would say is, well, there's an exponential in there, so we're going to need to have an e to the 4x. Okay, then it's probably a good thing to multiply that by an arbitrary constant. Or not arbitrary, we need to figure it out later. And you test that out, and it doesn't work. And you say, well, you know what, there's also an x inside of that right-hand side of the equation. So I'm going to introduce an additional constant, call it a1, and then let's try that. That looks pretty good. The derivative of this new guess, no matter how many times you take a derivative of it, you're not going to get anything different from what you started with. It's always going to end up being some constant, possibly with an x involved, multiplied by an exponential. But you try that out and it doesn't work. So then the next step is to say, okay, let's think about this again. What could have possibly caused this to be messed up? And the thing that happens is that there is a match between this 4 and the exponent of the particular solution and the 4 and the exponent of the complementary solution. So you throw an x in front and you try that, and that one works. Great. So that one, we had to introduce an additional factor of x, And if you go through the equations, it works. You can plug it in. Let's try one more before we go on to starting to get to harder things. Too many slides ahead. There we go. Find the form of yp for y double prime plus y equals x squared cosine of x. So again, you go through the complementary solution with the auxiliary polynomial, and you get that r is plus or minus I, which in turn gives you the complementary solution, arbitrary constant multiplied by cosine of x plus a possibly different arbitrary constant multiplied by sine of x. And now for yp, you go through and you make a guess. So I'm going to leave some space here because there's going to be a lot more writing in this time. So if this g of x on the right-hand side involves cosine of x, you say, well, I definitely am going to need to have cosine x. However, since this equation involves taking derivatives, I am also going to need to put in a sine of x, just in case. And I'm going to put in constants in front of each of those. You try that out, doesn't work. You don't figure out what a0 and b0 are supposed to be in order to resolve this particular solution. So then you say, okay, there's an x squared involved in there. I should include stuff that involves x squared, and since I'm taking derivatives of that in order to look at this differential equation, I should also include x. And you do that for both of these. So you have an a1x and an a2x squared. And then for the sine portion, you do something very similar. And that looks a lot better. It seems to include everything that could possibly happen with x squared cosine x when you take derivatives. But then you plug that in and it doesn't work. So the issue here, it turns out that it's because the yc contains a cosine and so does the yp. And then incidentally, there's also a sine for both of them. So you can multiply this entire thing by x and then it works. It's another situation. It's like dealing with repeated real roots for the linear homogeneous constant coefficient differential equations. You throw an extra power of x in there, and then it works. So let's try to create a formula for this. That's what everybody wants, right? What about the following differential equations? First one there, we've got y double prime minus y prime equals x squared plus 2x. Each of those things individually looks pretty simple, but it's two things added together. So these two are actually pretty similar looking. The next one, again, it's a second order differential equation, but in this case, two things added together, they look totally different. One of them is just a polynomial, it's just a constant. The other one is an exponential. Then the third one, it has the issue introduced by the second one, but in addition to that, it's a higher order equation. So we should be able to do all of these and come up with a way to um, do anything like this that involves polynomials, exponentials, sines, or cosines. So here's the main part of this. When you're dealing with undetermined coefficients, the g of x that's on the right side of the differential equation always involves pieces that look like what's inside the red box. There's always a constant multiplied by a power of x, multiplied by an exponential, multiplied by a cosine, and then plus a similar thing involving sine. So that looks super complicated, but it really isn't because you can break down all the examples that we've done so far in terms of those pieces that are shown here. And for myself, when I look at these problems, I always look at it in terms of this generic form here. And hopefully you'll see why too, because I think even though it makes it seem more complicated than what we just went over, it allows you to have a better understanding of more difficult versions of these problems. So from previous examples, there's a g of x equals 15. That was the first example that we did. I want to break down that 15 in terms of the various things that appear inside the red box formula. So first of all, there's no x's anywhere. So that means that m is equal to 0. The next thing is that there's no exponentials either. So that means that alpha has to be 0. In addition to that, there is no cosine, which means that beta is equal to 0. And then the only remaining pieces are C1 and C2. In this particular case, C1 is 15. And if you notice, um, because beta is equal to 0, the sine portion is gone, so we don't even actually know what C2 is. But I'm putting these in parentheses because those pieces of information are actually not as important as M, alpha, and beta, as we'll see shortly. So similar thing for 2x e to the 4x. There actually is an x here, so the exponent is 1. Still there, oh, there is an exponential. It's e to the 4x. That means that alpha is 4. And there's no cosine. Beta is equal to 0. And in this case, C1, let's see, because if beta is 0, this first portion still is there, so that means that C1 is 2. And then since beta is 0, the sine portion is gone, so we actually don't know the value of C2, but again, it's not going to matter. And then finally, the third one we did, there was an x squared, meaning that m was 2. There's no exponential there, so alpha was 0, or a real exponential. Remember that cosine really is a complex exponential, but I'm talking about real valued. And then beta, there is a cosine. It's cosine of 1x. So beta is equal to 1. And this says then that, well, C1 is equal to 1 because it matches the cosine. And there's no sine there, but beta is non-zero, so C2 has to be 0. But just like the previous two, that ends up not being super important. So that's summarized on this slide right here, the same information. Now what I want to do is I want to look back at the roots of the auxiliary polynomials. The first differential equation, remember, is 4y double prime plus 9y equals 15. We found that the roots of that were plus or minus 3 halves multiplied by I, square root of negative 1. But what I'll do is I will break that into real and imaginary pieces. And I'll do that for the other ones also. So we set each of these polynomials equal to 0, remember? So the second case, the roots were plus or minus 4, which are 4 plus 0i and negative 4 plus 0i. And then the third one we had plus or minus I, which is the same thing as 0 plus I and 0 minus I. Okay, the second and third ones we had to add an extra power of x when we made our guesses. Notice here that If you take, in the second example, alpha plus beta I, you get 4 plus 0I. There's a match there. And because of that, we needed to include an extra x. Same thing happens with the third one. If you take the alpha plus beta I, you get 0 plus I. There's a match. And you do the same thing, include an extra x. In the first one, that didn't happen. You had 0 plus 0I. And there is no match. So we didn't need to include that extra x there. We're slowly building up to something here. And that is the following, once again, very messy looking formula, but I think very helpful. When you deal with a g of x that has this form that we just outlined with the previous 3 examples that we did, you can make a guess depending entirely on alpha, beta, m, and this extra little piece here, s. So you always take something that looks like the thing inside that bluish, purplish box and make a guess that looks similar to it. The sum here means that you include the highest power and everything underneath it, 0 to m. And you do that for both sine and cosine. Remember the one with x squared cosine x? We included the constant, the x term, and the x squared term. The one that involved x, we put the constant and an x term. And the one that was just a constant, we had only the constant. The e to the alpha x takes into consideration the appearance of any exponential inside g of x. And this x to the s right here, that incorporates that in the previous 2 examples where we had to add the extra power. But it's possible that we might need to put more than one x in there. So s is the multiplicity of the complex number alpha plus I beta as a root of the auxiliary polynomial. This is where that multiplicity concept I mentioned comes into play. So now what we can do is we can revisit the 3 examples that we did from the perspective of this formula, and then do those 3 harder examples using the same formula. So once again, we go to 4y double prime plus 9y equals 15. 4r squared plus 9 equals 0 is our auxiliary polynomial equation. You have the roots are plus or minus 3 halves multiplied by I. Now on the other hand, you go to 15 and you write down the m, the alpha, and the beta, which we determined a few slides ago. And you take the alpha and the beta, combine them as alpha plus beta times I, which is equal to 0. That is not a root of the auxiliary polynomial. There's no match. And what that means is that s equals 0. So you tie it all together. You use that formula up here inside this that I'm circling. So x to the s, x to the 0, e to the alpha x. What was alpha? Alpha was 0. E to the 0x. Big set of parentheses. Beta was 0. Cosine of 0x. Now this sum here, remember m was 0 in this case. So this sum collapses to just one term, a 0. Do the same thing for sine. Sine of 0x. the sum collapses to just be 0. A whole lot of this stuff just goes away. X to the 0 is 1. E to the 0 is 1. Cosine of 0 is 1. Sine of 0 is 0. You're left over with a0. That's exactly what we got originally. And still, I think we're at the place here where you think, is this really making this any easier? It will. Let's do the second example. So you have the auxiliary polynomial. The roots were plus or minus I. And then x squared cosine x. We had m was equal to 2. There's no exponential, so alpha was 0. And then beta was 1. Looks like I skipped a slide. Always good to keep mistakes in here. I'm not perfect, but let's correct it. Let's do that example afterward. So y double prime minus 16y equals 2x e to the 4x. So r squared minus 16 equals 0. And the roots in this case are plus or minus 4. And then we go over to 2x e to the 4x. That one has m equals 1. There is an exponential, and there's no trig functions. So you gather together alpha and beta. That one is a root of r squared minus 16. So remember, r squared minus 16 is r minus 4 times r plus 4. So the portion that has the r minus 4, there's an exponent of 1. So that has a multiplicity of 1. So 4 is a root of r squared minus 16 of multiplicity 1. That means that there's a match, and s is equal to 1. Multiplicity 1. So you put that all together. You have an x to the s, x to the 1. E to the alpha x multiplied by cosine of beta x. So that's going to be cosine of 0x. And then in parentheses, you put in the polynomial that incorporates the m. So it has to go up to x to the 1 and include all lower powers. So you have a0 plus a1x and stop there. Add to that sine of 0x. Do the same thing with the b's. A lot of stuff cancels out and simplifies. So let's see, everything involving sine, so that's 0. This part right here is 1. So you get a0 plus a1x multiplied by x, so that's a0x plus a1x squared multiplied by e to the 4x. That's exactly what we guessed by reasoning out through multiple guesses and finding our way there. So now we can go back to the one that I mistakenly jumped to before. Y double prime plus y equals x squared cosine of x. So in this case, we've got alpha equals 0 and beta equals 1. So 0 plus 1i, which is equal to I, is a root of r squared plus 1. And remember, r squared plus 1 is r plus I times r minus I. And so that means that there is multiplicity of 1. And that means that there's a match and that S equals 1. So your particular solution in this case, you include the x to the 1, which was S. The alpha was 0, so it's e to the 0x. Now inside the parentheses, beta was 1, so you're going to have a cosine of x. M was 2, so you need to go up to x squared and include everything below that. So you have a0 plus a1x plus a2x squared. And then you need to do the same thing with sine, which suddenly is not 0 because beta is 1. So b0 plus b1x plus b2x squared. And of course, this simplifies a little bit because that's 1. And you can multiply the x through all of this. Well, let's not rewrite that. That's the exact same thing that we found by a little bit of reasoning earlier. All right, so hopefully you can see how that formula might help you, because we're going to tie it all together and do the complicated examples before where I said, well, what about these? So there's two things to keep in mind. One is that if two pieces of g of x share the same alpha beta pair, you just merge them together in the guess and use the larger of the two m's between them. Because if you don't do that, it's fine. It's just that you're going to end up with more equations and things are going to combine together anyway. So it's just saving some time. The other thing is that if two pieces of g of x have different alpha beta pairs, then you need to use a separate guess for each of them and add the results. So I created examples of both of those cases. Let's try that. For y double prime minus y prime equals x squared plus 2x. So first of all, auxiliary polynomial, set it equal to 0, and you get that r is equal to 0 and 1, and each of those, because remember you factored it to linear factors, each of those has a multiplicity of 1. Now break x squared and 2x separately, because those are independent of each other as far as g of x is concerned. Each of those we look at independently, m, alpha, and beta. For the first one, it has a power of 2 on the x, so m is equal to 2. There's no exponential. There's no trig function. In addition to that, let's look at 2x. So for that one, m is equal to 1, but it also has alpha and beta is equal to 0. So those have the same alpha beta pair. Par. Let's delete that. Pair. Same alpha beta pair. So we're going to use m equals 2, which is the larger of the two of them, and merge those together. So 0 plus 0i, alpha plus beta I, which is 0, that is a root of the auxiliary polynomial of multiplicity 1. So that means that since there's a match and the multiplicity was 1, s is going to equal 1. So we put that together. So on the outside of it, we're going to have an x to the 1 because s was 1. Exponential alpha x, alpha was 0, parentheses, beta was 0, so we're going to have a cosine of 0x. And remember, we're merging these together, so we're only using m equals 2. So you have x squared in all lower powers of x. Do the same thing for sine. use different labels for the constants. Remember, you don't want to reuse A0 and A1, etc. because, um, and as I said that, I wrote A2 instead of B2 because these are all going to be different, most likely. So the sine portion is gone anyway, because sine of 0 is 0. Exponential is 1, cosine is 1. So it's just x multiplied by that polynomial involving the a's. That's your guess. So that's, not particularly difficult, I guess, once we establish that formula from the previous slides. Let's try another one. Y double prime plus y prime minus 6y equals 1 plus e to the 2x. Same procedure. Auxiliary polynomial r squared plus r minus 6, set that equal to 0. And if my calculations are correct, this is r plus 3 times r minus 2. And you get that the roots are minus 3 and positive 2. And each of these has a multiplicity of 1 because of the linear factors that have an exponent of 1. Okay, now let's break apart two separate things added together, each of them going to have its own m, alpha, and beta set. So the first one is just a number, so there's no x's. There's also no exponentials. There's no trig functions. So first part, alpha plus beta I is 0 plus 0i. Actually, let's outline the exponentials pieces too before we jump ahead of ourselves there. It also has m equals 0 because there's no polynomials there. It does have an exponential, alpha equals 2, but it doesn't have any trig functions, so beta is 0. So they're different alpha beta pairs. So we have to consider each of these independently. So the first one was 0 plus 0i, which is 0, and that is not a root of r squared plus r minus 6. So for that one, there is no match, meaning that s is equal to 0. However, for the other one, 2 plus 0i equals 2, that is a root of r squared plus r minus 6, and it has multiplicity of 1. So therefore, that one does have a match, meaning that since the multiplicity is 1, s is 1. So we need to create two separate pieces. Let's do that. So the first one here is going to have an x to the 0 because s was 0, alpha was 0, parentheses, beta was 0, so you have cosine of 0x. M was also 0, so you only go up to a0, and then do the same thing for sine. Now on the other hand, you have to do a completely separate one for the e to the 2x portion. So that one has an s equals 1, so you put an x to the 1. It has alpha equals 2, and it still has m equals 0 and beta equals 0. So you have cosine of 0x. Now be really careful here to not name it the same thing. So I'll just put a symbol tilde over the top to make sure that that's different from the other a0. Same thing for the sine portion. And this simplifies quite a bit. Let's see. All the sine stuff goes away. In the first one, there is only an a0. All the rest of the stuff is either 0 or 1. And in the second portion, there's an e to the 2x, there's an x, and there's an a0 tilde. That's your guess. Two separate guesses added together. That one works. Okay, now for the grand finale. Let's work with a fourth order differential equation with a complicated g of x. So if you haven't seen higher order equations before, they work exactly the same way. You have an auxiliary polynomial that has powers of r matching the derivative orders. So the auxiliary polynomial here is going to be r to the fourth minus r squared, and you set that equal to 0. So I put a higher order equation so that we could look at multiplicities that are higher than 1. So this factors to r squared times r plus 1 times r minus 1, and you get 3 roots, 0, minus 1, and 1, where notice that the r minus 0 term has an exponent of 2, so that one has multiplicity of 2, while the other ones have multiplicity of 1. And in case you're curious, what that means is that the complementary solution is going to look like this. It'll be a constant multiplied by e to the 0x plus a constant times x multiplied by e to the 0x, and then another constant multiplied by e to the minus x plus yet another constant multiplied by e to the x. So the repeated root has you put an x in there, like you probably already know from the second order equations. But anyway, that's just a parenthetical statement. So if you focus on 4x on the right-hand side, m is 1. There's no exponential, alpha is 0. There's no trig function, beta is 0. Combine those together. 0 plus 0i equals 0. That is a root of r to the fourth minus r squared, and it has multiplicity of 2. So that means that there's a match, and s is equal to 2. Okay, now let's try to do the same thing with the other piece. M is 1 again. Alpha is minus 1. Beta is 0. Different alpha-beta pair. And in this case, you do negative 1 plus 0i, which is minus 1. That is a root of r to the fourth minus r squared, and its multiplicity is 1. So again, there's another match, but in that case, s is equal to 1. So we can assemble our yp using the formula. For the first part, the 4x, there's an s equals 2, so you're going to have an x squared on the outside. Then you do e to the alpha, e to the 0x. Beta was 0, so you're going to have a cosine of 0x. M was 1, so you go up to the x power and include the constant term below that. And then you do the same thing with sine. So you have b0 plus b1 x. Close that set of parentheses. Underneath that, you have a separate portion of the guess for the other piece. That one had s was equal to 1. It had alpha equal to -1. And it had beta equals to 0 again. So cosine of 0x. And again, be careful about the labeling here. I'll just put tildes over everything to make sure that they're different. So sine of 0x. Same thing with b0 and b1. So tons of stuff cancels out or ends up being 1. All the sine stuff. Let's see. So what does this end up being? In the first piece, there's going to be an a0 multiplied by x squared and an a1 multiplied by x cubed. That's all for that part. And in the second piece, there's going to be an x to the 1 multiplied by everything. But there's also the e to the minus x. So that's your guess. And there you go. These can be very difficult when you first try to tackle them. But if you break them down, and I think it's very helpful to break them down into that m, alpha, and beta pieces, and then establish the value of s. And after that, it doesn't seem as bad, at least to me anymore. So I hope that if you sought this out for extra help on undetermined coefficients, that this helped you. And maybe I'll make some more videos coming up. So thanks for watching.